you elevate the temperature. And these are three very, very important stages. The first one is that after you finish cold working on this workpiece, you just introduce some, this is the residual stresses, right? Residual stresses, however, and then it will elevate the temperature, so there will be recovery. Recovery means that the stress in the highly deformed region are released, are relieved, somehow, somewhat, and the number of mobile dislocation is reduced. Yeah, this if you elevate the temperature. So this is one stage. And the stage number one. The stage number two is recrystallization. So at some temperature, they will have new equal X. This is the stream frame grains are grown. So what is equal X? Can somebody tell me? As the name suggests, it's very the name equal X. Equal X means that it's almost a circle, and this grain in almost all the directions they have the same dimensions. Okay, this is an equal X. And the stream frame grains, so because the temperature after the recovery stage is completed, so this the stream is smaller, and finally it's fully free. And replacing the older grains. Now you have new grains. Replacing new grains. So this temperature occurs, and this is recrystallization occurs in this interval, 0.3 Tm and 0.5 Tm. And Tm is the recrystallization temperature. So it is generally defined as the temperature at which complete recrystallization occurs, and within approximately 1 hour. So this is a very, very important word. 1 hour. 1 hour. This condition must be met, and so you can just guess this is recrystallization temperature. It decreases the density of dislocation and lowers the strength of material, but the ductility is increased. So, and here are several commonly seen metals: lead, tin, cadmium, and zinc. And they recrystallize at about the room temperature. So this is the kind of special. I hope you guys know, pay attention to this for the commonly seen the metals. So after recrystallization, and there is a grain growth. The new grains keep growing. So if we continue to raise the temperature of the metal, the grains begin to grow, and their size may eventually exceed original grain size. So we have 3 stages. You need to know these 3 stages. So this is the temperature's influence on this grain size, the strength, hardness, ductility, and residual stress. You can see residual stress decreases substantially as the temperature increases, strength and hardness decreasing. Right? So, however, ductility, as I said, ductility is kind of competing with strength. The strength decreases and the ductility increases. So the grain size, this is cold worked. And after the recovery, so there is new grains here. And then finally, this new grains keep growing, and you have a bigger grains. Well, you can see the bigger grains. Any questions so far? So my bottom line is that you know what these 3 stages are, and use your own words to explain on how they work. Right? This is just a sketchy idea. When you take the material science, and you will learn a lot of details. So the recovery for this, the time is important also. The time, the strength and hardness, the time, the strength and hardness, and also this elongation here. Right? So this is is very, very important. So what is recrystallization? There are several observations here. So for constant amount of deformation by cold working, the time required for recrystallization decreases with increasing temperature. So the time, if the temperature is much higher, the time required for recrystallization will be shorter. So this is understood, right? So the more prior cold work done, the lower temperature required for recrystallization. So next one is the higher the amount of deformation, the smaller resulting the grain size during recrystallization. So this is the deformation can refine the grains. And anisotropy means isotropy, not isotropic. Anisotropy due to preferred orientation, usually the position of the recrystallization, a temperature higher than the required for recrystallization may be necessary to restore this isotropy. Isotropy means that the mechanical properties are identical in all directions. Anisotropy means that this is the mechanical properties in the directions for given point are not identical. And then we talk about this homologous temperature. There are three. Last time I think I introduced the two working conditions. One is hot, one is warm. But sometimes people introduce the hot and cold. And here is the third one. And you can see. So the demarcation line is the recrystallization temperature. So it's hot working. This plastic deformation is carried out above. This is the recrystallization temperature. So here is a cold working. So this is the above. This is recrystallization. It's carried out. This below the crystallization temperature. And so this is below. Okay. So this is below. I'm sorry. So this is the type of. And warm working plastic deformation is carried out at intermediate temperature. So the demarcation line is the critical, the threshold is the recrystallization temperature. Questions? And what is the TM, guys? I forgot it. Can somebody remind me?
Isn't that the moles?
Melting temperature. Right? TM is the melting temperature. And homologous temperature is the operating temperature, the ratio of the operating temperature and to this is the melting temperature. Now we talk about failure. See, the failure. So here is the tensile A, B, C, D is the tensile, and we have different failures. Failure here is the necking. Is the necking. Necking and fracture of the ductile material. Whenever you see this kind of failure mode, you can say that this material is ductile. This one, second one is a buckling. This is buckling. This guy is subject to the compressive loading. So if this beam is long, it is the buckles is a very important problem. The buckling of ductile material and the compressive load. And third one, this one, fracture of brittle material is a brittle material and the compression. So you can see this is almost 45 degrees here, right? And last one is the cracking on the barreled surface of ductile material. So this is the barreled surface, this barreling. So this is the cracks. So this is the commonly see the failure mode. So here is the intention. Right? So this is the intention. Here. Are you taking the mechanical solid lab? You will do this test, the tensile test. You will be given three specimens. One is a cast iron, one is ductile, one is aluminum. Steel. Aluminum and steel, they are ductile. And the cast iron is brittle. But the brittle material fails this way, right? So this you have almost two very flat surface in here. So here the ductile material usually is this one. So this is the brittle material in polycrystalline metals. The specimen you get, and usually they are polycrystalline metal. Polycrystalline metal means that they have a lot of the grains there. So this is shear fracture in ductile, the single crystal. This is 45 degrees. This is single crystal. The third one is ductile COP and COM fracture in polycrystalline metals. For this one, COP and COM, COP and COM. Right? So for the Dato material, and usually they break this one. It's very hot in this room, is that right? I hope I'm not ill. Are you sweating now also? No? You are more healthier than me. Okay. So this one, okay, whenever you see the COP and the COM, this kind of failure mode, and you can 100% sure that this material is Dato. Understand? So always, this is COP and COM. When they break, they have this. This is lower end. This is upper end. So usually this is a 45 degree and this is 45 degree. Theoretically, but just a little bit of variation based on the defects, the content of defects in the specimen. So this is a C. D, and D is completed Dato material in polycrystalline. So this with 100% reduction of area, completed Dato. So this, we seldomly will see this one. Right? So this one is an extreme case. That its material is very, very Dato. So based on these slides, I want you guys to be able to understand for tension on what kind of failure mode you can see for brittle material, what kind of failure mode you can see for the Dato material, for tension under this is under compression. Dato fracture surface. This one is the very microscopic. This surface of Dato failure in low carbon steel and showing the depots. And fracture is usually initiated as impurities. Impurities include the different items in this material. Also inclusions are all pre-existing voids. The depot, right? Depot is kind of cup, little bit cup, the cup, a small cup. So whenever you see this one, this is the Dato fracture surface. So uniting under fracture. So when you have a tensile load, so usually it's the first stage, it becomes smaller, cross-section area becomes smaller, and then you will have small voids forming here, forming this way, and then these voids will be connected together, become a big crack, and finally it comes this way. Okay? This is usually this 45 degree. The COP and the cone is a fracture. Usually here, this angle and this angle is 45 degree. Then we talk about effect of inclusions. And if the material is not very, very pure, there are some inclusions. Impurity. We can treat inclusions as impurities. And inclusions have important influence on Dato fracture and the formability of material. Formability of material, this is for metal forming. We have the raw material, we can just compress it and or draw it to get some certain form of final products. So this is the formability, okay? Metal formability of the material. So they may consist of impurities of various kinds and second phase particles. And second phase particles means that, even though here for the titanium, we have alpha and beta titanium at the very beginning. But as the temperature goes, we might have the alpha prime. Alpha prime is called second phase. Right? So the second phase means that under some condition, the original phases just change to a new phase, and these new phase or phases are called second the phase particles. For example, oxides, carbides, and sulfides. The greater the volume fraction of the inclusion, that means the more conclusion, the lower will be the ductility of material. This is the lower of the ductility. So here, this is the matrix of the body material, main material. Suppose we have inclusions here, and so this is inclusion. This is a soft inclusion. This is a hard inclusion. If it is very hard, right? If this inclusion is harder, then this is the matrix material. If you compress it, and there will be a gap there. So this is a hard inclusion also, and this is the voice here. In this direction, the strong direction, and in this direction is the weak direction of the deformed metal. Why? Because in this direction is perpendicular to this is your the fellow. So transition temperature and the spin engine. This is transition temperature. It talks about at what condition the material becomes brittle from the ductile or vice versa. So here, this is a narrow temperature range. Here is a narrow temperature range across which the behavioral metal undergoes a major transition. Here, this is ductility. Say suppose this is temperature, above this temperature, the ductility is much higher than the one associated with the lower temperature. So this temperature is called transition temperature. So this occurs in 40 centimeters cubic and some hexagonal closed packed metals. So this is the transition temperature at which and the ductility changes substantially and is dependent upon the composition of your material, microstructure, grain size, and the surface strain, and shape of specimen, and the rate of deformation. So there's a lot of the factors that can influence the transition temperature. Now you should know what is the transition temperature. Transition temperature is the temperature at which the ductility of my material changes substantially from the ductile to brittle or vice versa. So this is called transition temperature. So another one concept is a strain agent. And strain agent, here is a true strain, and this is a true strain, and this is a true stress. Strain agent means what? Means carbon atoms in steels separated to dislocations, thereby pinning them and thus increasing the resistance to dislocation movement. It results in the increased strength and reduced temperature. So always the strength and the ductility, and they are competing with each other. Right? High strength means low ductility. Low strength means high ductility. Any material cannot possess both high the properties, both high strength and high ductility. It's a strain agent. It's the strain of the strain becomes bigger, the true stress becomes increases also. It's called a strain agent. Then we see the brittle and the intergranular fracture. This one is the from the steel. Typical fracture surface of the steel that's filled in a brittle manner. Why? And what condition they can fill in a brittle manner if the temperature is low, right? If the temperature is very low. And you can see the difference between this one and the previous one I just showed you. That is dominant. This is the dominated with this is the dimples. Here. Well, question?
Did you say that the difference between that photo and the previous photo is
Yeah.
the temperature difference?
This one is also for the steel. Steel is a ductile material, but this guy under some condition it can fill in the brittle mode. So what is the condition you already see that a steel can fill in the brittle manner instead of the ductile manner, low temperature. Right? So here it is this intergranular fracture and two different magnifications. So intergranular, what is intergranular? As the name suggests, intergranular means that between the grains, right? Right? Inter means international. International means related to the multiple countries. So this is related to multiple grains. You can see the fracture is a grain granular, right? It's the grain just almost the grain, the whole grain is off. That means the rupture of material happens in the grain boundary. It's called intergranular. The grains and the grain boundaries are clearly visible in this microscope. See? This is the grain that is off from this body, and you can see this grain boundary. So these are two different magnifications. So this is much bigger than this one. The fraction mode. This is a fraction mode. Yeah, a lot of facts, guys. Okay, so let's read for this course the exams given as a take home. Fraction model. I want you to know what's a fraction model. Fraction modes. We have three modes. The first one is model one is opening. First one is opening, and second one is sliding, and third one is tearing. Okay, so this is material. If my material open this way, this is the load. Okay, if it open this way, the crack goes this way. So this is called opening. So the mode one, red dominates. I want you to know, even though this is, I will not talk about this in detail, but I feel this is a basic fact. Mode one means opening. See, this crack opens this way. This is a crack, okay? This is a crack face, and this is another crack face. Opening means open this way. So mode two is a sliding. Mode two, the sliding means that this is crack surface, this is crack surface. In this way, right? This way is sliding. Mode three is tearing. Tearing means this is like cracker phase one. This cracker phase two. It goes this way. Is the tearing. Mode one is opening. And mode two is sliding. And mode three is tearing. Tearing means that it happens in not in this in this direction. So this is opening. So this is sliding, and so this is tearing. Right? So you can see. And this is the tearing, it happens this way. And so this is very, very important. So this is related to the, we will talk about this one in the CAE and also in the machine design and also in the fracture mechanics, which is a graduate course. If you are mechanical engineer students, and you might take CAE with me also, machine design with me also, mechatronics with me as well. So here, typical fracture, fatigue fracture surface on metal. This is fatigue, and the beams, bench marks most components in machines and engine fueled by fatigue, not by excessive stack loading. You know fatigue, right? You know fatigue. Fatigue means that the specimen and you apply the load cyclically, repeatedly. So for example, if I have a beam, maybe suppose this is a shaft or beam, I bend it this way, and this way, and this way. Right? As the time goes, even though my bending moment, the bending strength resulted from this bending moment is very, very low when compared with the strength of material. However, as the time goes, if this after many cycles, and this specimen still fails, and this is called fatigue. Sometimes fatigue means the number of cycles plays a very, very important role. And even though my bending stress is very low, but as long as the number of cycles is high enough, this component is still is going to fail. This is called fatigue. This is fatigue. This is a reduction in fatigue strength, and this is the ultimate tensile strength. So this for different manufacturing processes, right? So S-cast is the surface is very rough. The fine polish, the surface is very smooth, just like a mirror. So for this case, the fatigue life is very high, fatigue strength. But for this, the fatigue strength is low. Why? Because there are a lot of pre-existing cracks on the surface. And if there's a cracks, if you apply the cyclic loading, and these cracks will be propagating. And finally, it fails. Are you following me? Okay, good. So this is, you can see different manufacturing processes: fine polishing, grinding, fine tuning, turning, rough turning, S-cast. S-cast is means there might be a lot of pre-existing cracks on the surface already. Right? So this is number of cycles here. The stress amplitude. This is stress amplitude is the cyclic loading. How much stress you apply, and so this is number of cycles. This is number of cycles, and usually 10 power 6 is 1 million. So we use this one as a threshold. Right? Use this one as a threshold. If your specimen can experience much higher than this one, that's very awesome. But usually it's 1 million number of cycles is used as a reference. And we will talk about this one in detail in the CLE class. Are you taking CLE class this semester?
I take it next semester.
Next semester?
They do. Yeah.
You are taking?
I took it.
Okay. The fatigue strength. My fatigue strength can be improved by the following means. First, introducing compressive residual stress on surfaces, and this is what I told you, right? And by some means, if you induce compressive residual stress on the surface, and you are increasing the fatigue life of the component. Why? Because compressive residual stress prevent cracks from initiating and propagating. The third, this can be short pinion, rolling burnishing. Rolling burnishing is cold working. One means of cold working. Rolling burnishing. And short pinion means that you know what short pinion is. Short pinion it means it is a gun. Okay, the gun. And this is if you pull the trigger, a lot of small particles will come out, and these small particles will be projected on the surface of your material because the impact of these small particles, metal particles, and you will have a lot of the craters on the surface, right? So these craters, each of craters will be compressed, so and you will have a lot of the residual stress, compressive residual stress here. And as a result, the fatigue life is enhanced. So this is called short pinion. And we use using the pinion guns and to improve the fatigue life. So also we have a laser pinion, right? Laser pinion is laser pinion. And I'm doing this research. So laser pinion means that we use the laser beam. And we use the laser beam to heat this workpiece. Because the laser, when the laser interacts with this material, and there we will have high temperature, right? So the air there will conduct this ionization and also pressure. This generates pressure, this high pressure, and will act on this workpiece and to induce this compressive residual stress. Right? So we have two pinions and two pinion methods. One is a traditional one, is called a short pinion, and you can get this is the pinion gun in the Lowe's or the Home Depot. And all the laser pinion, I'm doing this research. If you are interested, and I can show you around in my laser pinion lab. Right? So this is very good. So case hardening by various means of heat treatment. And did I tell you this case hardening? Did I tell you? Okay, case hardening means that we have a chamber, right? And you have a specimen, you put the specimen in the chamber, and then at the same time, and you put some carbon-rich, this is either liquid or gas or solid, and let this your specimen to interact with this is the liquid, solid or gas that are rich in carbon atoms. And then you elevate the temperature. After you elevate the temperature, there's a lot of carbon atoms from all the either liquid or solid or this is the gas, and will come to the surface of your workpiece. Right? As a result, the hardness of your workpiece will be increased, and at the same time, compressive residual stress will be induced. Who can just reiterate what I just told you? Will.
I think you said you put your material inside a compartment that has liquid or solid and increase the temperature, the atoms come in contact with it and cause compressive residual stress.
Yes, right? Yes, the several important things. First, so the chamber, the silver chamber, and then you put your workpiece here. At the same time, you put either liquid or solid or gas that are rich in atoms, in the carbon atom, in carbon atoms. So let these liquid, solid, or gas to interact with your workpiece. And then you seal the chamber, then elevate the temperature. After some time, some carbon atoms from around in the chamber will come to your workpiece. As a result, two things we can accomplish. First, the hardness of the workpiece is enhanced. First thing. Second, and the residual stress, compressive residual stress, will be induced on surface by the carbon atoms. So as a result, the particular application. So I will test your understanding of this one. Okay? If you are not sure how to answer this one correctly, and you can just email me. Now that I will ask you this one. So the third means is that providing a fine surface finish to the part, thereby reducing effects of notches and other surface imperfections. So this way, surface finish, if the surface is mirror, that'd be very, very awesome. Why? Because you just eliminate the pre-existing cracks as much as possible. So the fourth one is selecting appropriate materials and ensuring that they are free from significant amounts of inclusions, voids, and impurities. That means the purer of the material, the better for the fatigue light. So this is 4 ways that people commonly use to improve fatigue strength. So these are physical properties of material, the metal, and these are non-metallic. So density, melting temperature, specific heat, thermal conductivity, coefficients of thermal expansion, and specific. Okay? You will see a lot of the term that contains specific. Whenever you see specific, that means something per unit volume, right? Density. the effect of carbon on steel property. The carbon, we know that the carbon contains, the steel contains carbon and iron, right? Right? Okay, so this is the carbon percentage. So this is a carbon percentage. For 0 means that this is a pure iron. Pure iron is usually it's not very useful because the hardness is bad. And then we increase the carbon content. But if the carbon content is very high, that is another story. Right? Don't go to two extremes. So this is one extreme that is pure iron, and this is another extreme is a pure carbon. Pure carbon is cannot be used for industry purpose. You understand? Okay, so you can see impact energy. So this one elongation, yield strength, tensile strength. If the carbon, the more carbon, this one is higher. So as I said, strength and the ductility, and they are competing. So low carbon, medium carbon, high carbon. So in the material science class, you will learn this one in detail. So a new stainless steel. What is the stainless steel, guys? What is one of most important the alloy for the stainless steel?
Chromium?
Huh?
Chromium?
Chromium, yeah. What is the percentage of chromium and you need to have stainless steel? Okay, 12. Some textbooks say 11. I'm going to say let's follow this one. 12. Okay. I don't know why they changed this one. A new stainless steel. So here is AISI. This is the stainless steel. So these are characterizations and the typical applications, and you can take a look. The stainless steel is a relative word. Okay, it does not mean that no matter under what condition this guy will stainless. No, it's not true. That means it is take a longer time for this material to be eroded completely. And tool and die material, we can imagine for tools and dies, and the material must be very hard. Do you agree? Otherwise, you can just change the role. Right? Suppose you want to use this tool to cut something else, but this guy is very soft. And who is tool? Who is the workpiece? You change. So here, for high-speed machining, and you use molybdenum-based all this tungsten. Tungsten is very hard. And the cutting tool, usually we see a lot of tungsten carbide. Tungsten carbide is commonly used cutting tools in machining. And for hollow work, and they use these H. So this is the tool, the die. Okay? Hollow work, the die must be very hard. If the dies are not hard enough, the die deforms first. That's very funny. So cold work, and they use a high carbon, high chromium D level. This is the D series, A series, and O series. And shock resisting usually have more carbon. Mold steels very high. Right? So this the hardness is very high, very strong. Special purposes, you use the low alloy and use the carbon, the tungsten. This water hardening. And use the tungsten carbide. I'm sorry, this is a W. So here is a process based on the different processes, and you select on different materials. Let's see, because I'm a machining guy, you can see the machining thing. For machining, and we use carbide, high-speed steel, ceramic, diamond, and cubic boron nitride. Cubic boron nitride is the newest one. When compared with other materials. Okay? Carbide is commonly used. The tungsten carbide is also commonly used. So this is machining. And because I'm a machining guy, as I said. So there are other things, roller, sheet metal. This is forming. This is forming process. Coiling, extrusion, forging, and these are metal forming, and so this is the machining. And what's the difference between machining and the metal forming? Can somebody tell me?
Machining is a subtractive process. Take away material when you machine.
Yeah, right. So machining means that the chips. I'm not talking about the food chips. I'm talking about the chip. You know chip, right? And you just cut something off from the main body of the material. This is called a chip. In this case, it's machining. Otherwise, is a deforming. You want to get the final product by the compressing, extrusion, or these kind of things. The severe deformation, that is metal forming. The difference is that whether you have crack or whether you have this is the chip formation or not. If this is a chip formation, machining. No chip formation, metal forming. So here is the non-ferrous alloys in the aircraft. This is engine. So this is they use titanium. Titanium alloy for the fan. Titanium alloy for the compressor. The titanium or nickel alloy high pressure compressor. Nickel alloy. Turbine is a blaze nickel alloy. Aluminum alloy for this one is inlet. The case we use aluminum alloy. So this is, you can see, these non-ferrous alloys. They are very useful for the application of at high temperature, elevated temperature. So aluminum alloy are usually also commonly used one because they are kind of cheap. So by the way, this pure aluminum is almost useless, right? I'm sorry, not useless. This we don't apply the pure aluminum often. Pure aluminum alloy. Pure aluminum is too soft. This is wrought aluminum alloy. So this is different. These are labels. This is labels here, and these are characteristics in terms of corrosion resistance, machinability, and weldability. Weldability means that, and how easy the difficulty it is. The difficulty when you the degree of difficulty and you weld. This is the aluminum alloy together. This is weldability, machinability. So these are typical applications. I will not read this one. You can just take a look. So magnesium alloys here, magnesium. And so these are the typical forms: extrusion, sheet, and place, extrusion, and forging, sheet and place, extrusion, and forging. So the different automated strengths, use strengths, and elongation, and they are given here as well. Copper and brass. Copper is very important also, but it's not very commonly used one because the strength and hardness. Brass, the bronze, and you can take a look. And nickel alloys are very popular now because the hardness, because the strength at high temperature. Nickel alloy and titanium alloy. Nickel-based super alloys. See, the name, give the name super alloys. Icono is the commonly used one. Also, another one is Mosploy. And there are a lot of people are doing research to investigate the machinability of this guy and this Mosploy. Titanium alloys is very hot in the past 20 years. Not still, and titanium alloys